Hello, my name is Michael Schmied from the Technical University of Graz, and today I want to present our paper about a patch-based approach for aortic landmarking. First of all, this paper is based on the work of Yuan et al. Called Fast Multiple Landmark Localization using a patch-based iterative network. It was used to find landmarks in 3D ultrasound images of the fetal brain. Our goal was to check how these methods behave with ill-posed landmarks, where there is no strong feature near them, like the aorta. I would like to start with an explanation of what a landmark is. A landmark is an anatomical structure or location which is used as a point of orientation. For example, if you find the entrance of the heart, you know that this is the beginning of the ascending aorta. This is useful information which can be used for tasks like the detection of anatomical structures in diagnosis, or for segmentation, or for feature-based image registration. One of the challenges here is that landmarking is a time-consuming task, which is generally done by hand, step by step, so each landmark has to be placed individually. This procedure leads to another problem. The local positioning of landmarks is highly variable due to the diverse perspectives of different observers. This means there is no guarantee that one point in the eyes of one physician is in the exact same spot as another physician would see it. And of course, the last challenge here is that to properly set landmarks for many scans, there is a need for trained medical physicians, which is always related with high expenses. A solution that was found in the last years was that we could use convolutional neural networks for landmarking. In our case, the CNN was used to detect 4 landmarks of the aorta, which will be later explained in more detail. It was implemented with the programming language Python and the machine learning library PyTorch, working on the GPU using CUDA. We got some challenges here as well, like for example, the limited amount of medical image scans which is used to train the CNN. Or another challenge was the local variation of the positioning of landmarks, like I mentioned before. The reason for this is that the CNN needs proper ground truth data to train with, so the variation should be as low as possible. The data which is used here was acquired from an article of Masoudi et al. And from the CAT-PE challenge. Of the 75 CTPA scans which were at disposal, 60 scans were used for training and 15 for evaluation and testing. CTPA here stands for Computer Tomography Pulmonary Angiogram, which utilizes computer tomography and the usage of a contrast medium to record an image of the pulmonary arteries in the human thorax. The landmarks were manually placed with the help of the client-server-based online environment StudierFenster. The first landmark was positioned near the entrance of the heart, the second one on the aortic arch, the third one on the descending part of the aorta on the same height as the first landmark, and the last one was defined as 6 slices from the bottom of the scan. An important method which was used in this thesis is principal component analysis. PCA is used to reduce dimensionality of data and extract features from it. It is a linear projection of data onto a lower dimensional subspace where the average projection cost is minimized. The original 2D data, here marked as red dots, is projected onto the lower dimensional 1D subspace, indicated by the magenta line. The average projection cost is indicated by the blue lines and is defined as the mean square distance between 2 points. PCA was used here to transform the landmark coordinate data onto a lower dimensional space, so that the amount of features that has to be calculated by the CNN is reduced. X stands for the original landmark data, X bar is the mean of the data, W are the eigenvectors of the data, and B is the projected data in the lower dimensional space. The patch-based CNN, which was implemented, predicts multiple landmarks in the aorta at once. It uses 2.5D image patches as input, which means given a random point in a volume, 3 2D image patches with the size of 101 × 101 are extracted and concatenated as a 3-channel 2D representative patch. This reduces computational effort since only 2D convolutions are needed. The network combines a classification and a regression task in a joint network. We can here see the implemented loss function, where the first part represents the smooth L1 loss for the regression task, while the second part of the equation represents the cross-entropy loss for the classification task. The parameter alpha defines the weighting of the 2 different losses. In our case here, alpha was set to 0.5, so both losses are equally weighted. The combination of the two tasks prevents model overfitting, increases model accuracy, and improves the generalization of learned features. The regression task estimates the amplitude of movement of a randomly initialized point towards a landmark. This means for each axis there is one element in each displacement vector for each landmark. The classification task, on the other hand, estimates the probability of a landmark to move in a certain direction. For this task, the estimation is divided into 6 different categories, positive and negative along each coordinate axis. On this slide, we can see the network architecture of the CNN. The network is comprised of 5 convolutional layers, each followed by a normalization layer, a ReLU layer, and a max pooling layer, which are all shared by the classification and regression task. After the 5th pooling layer, each task has 3 separate fully connected layers. Each of them is followed by a ReLU layer and a dropout layer, except the last fully connected layer of each task. All convolution layers use 3x3 kernels with a stride of 1, and all pooling layers use 2x2 kernels with a stride of 2. Now the movement of a randomly initialized point towards a landmark can be defined by the following equation. Xt defines the position of the point before the movement. Xt plus 1 is the new predicted position closer to a landmark. Pmax defines the highest probability of the classification task, and d defines the movement from the regression task. Simply put, a point xt is moved by a certain amount in the direction of highest probability towards a true landmark, as can be seen in the pictures below. The training of the network was stopped after 3000 epochs, which took around 60 hours. We can see from the curve here that the loss decreases over time and starts to converge. For the evaluation, there were 2 important parameters which had to be defined. The first one is the amount of inference steps the network takes to move a point to a landmark. The second one is the amount of random point initializations. The mean over multiple initializations result in the final landmark prediction. An example is shown in the picture below, where 3 random initialization points are moved in one inference step towards the true landmark. The accuracy of the network was tested for 1000 independent predictions of all 4 landmarks for different amounts of inference steps and initializations. We can see from the table that the best result was achieved with only 1 inference step and 50 initializations. 99% of the predictions had an error that was closer than 30 mm for this setting, and we got a mean of 16.04 mm and a standard deviation of 5.6 mm. The results depicted in this table indicate that the error decreases with an increasing amount of initializations and fewer inference steps. To conclude, the network was able to predict landmarks within a certain amount of error. The accuracy should have increased with more inference steps, but this was not the case here. A possible reason could be that the CNN was not trained equivalently with far away and close enough random points. So after the first iteration, due to the high network output, the probability of the network to predict a point far away is higher than to predict a point closer to a true landmark. Some sort of movement penalization for an increasing amount of iterations might bring an improvement, because smaller movements might then actually move a point closer to a true landmark. Possible areas of improvement include attaining more data to train the CNN with, letting professional medical physicians do the landmarking, resize the medical volumes so all have the same size and are isotropic. Different batch and patch sizes could also influence the network's performance, and we could train the network for a higher amount of epochs and penalize the movement of landmarks with an increasing amount of inference steps. Here we can see the best result of a CNN prediction in 2D, where the red dots indicate the true landmarks and the green dots indicate the predicted landmarks. This plot shows the CNN prediction in 3D, where the red dots again indicate the true landmarks and the green dots indicate the predicted landmarks. The plot indicates that the predicted landmarks near the entrance of the heart, the descending part of the aorta, and 6 slices from the bottom are closer to the true landmark than the landmark on the aortic arch. This shows the performance of the algorithm on ill-posed landmarks, Since the aorta is just a tube with no strong features on which the algorithm could really rely on to get a higher accuracy. The algorithm was implemented on studierfenster.tugraz.at as well, where one can try it out themselves if interested. If we go to the web page, we will find the medical 3D viewer, where we can press the Select Files button to open a medical image file. We use one of the test files in the NRRD format here and open it. This way, we will open the volume in the 3D view, and on the side we get additional perspectives as well. We can turn the volume around and select a different view. We will take the first one here and go to the subpoint landmarks, which we can pin to stay visible. Next, we press Calculate Landmarks and wait for the algorithm to finish. A notification will appear saying landmark successfully loaded, on which we just press OK. If we then scroll down the volume, slice by slice, we will find the first two landmarks, which are on the descending part of the aorta and near the entrance of the heart, here and here. If we further go down then, we can use the bar scrolling on the top of the window as well, until we reach 6 slices from the bottom. We will finally find the third landmark here, right here. Lastly, we move up to the aortic arch, the last landmark, and it becomes visible right in the middle here. By now pressing Download Landmarks on the left side, we can save them in a .csv file on our local computer. We can name the file however we like, press the Save button, and we are finished. Finally, we want to thank you for your attention, and we want to thank all our supporters for their support.